Hey everyone, so the purpose of this video is to cover triggers, counters, and timers in Proficy Machine Edition. We're using version 9.5 and we're programming an Emerson RX3i PACSystem controller. That's the IC695 CPE 305. So without further ado, let's get started. Now I have my Proficy Machine Edition environment open here. I've got a very simple program, just a power supply and a rack along with my CP305 and a network module. And I have one program block, which is my main routine, with nothing inside it. So it's kind of like a blank canvas and will give us the flexibility to use our instructions. So let's start off with triggers. We're going to use what's called the rising edge trigger or R trigger instruction. So I'm going to jump to my PLC ladder, category, choose instruction, and just type in R trig. And then once that's created, because we're making some online changes, I'll just say OK because I'm entering test mode. And then let's give this function block a name. Let's call it R underscore trig instance. So okay, so I already have an instance defined, but you can go ahead, you can call yours R trig. And I'm going to just do comma G to make this a global variable. Now on the left hand side, I'm going to just ensure we have power flow from left to right to ensure the instruction gets executed when the PLC scans this rung. And then on the left hand side, I'm also going to put a normally open contact with a variable. Let's call this execute underscore trig, or execute trig rather. And the reason I'm doing this is because the rising edge trigger, or trig, it detects a change of state based on the input. And it produces a single pulse whenever there's a rising edge, meaning the input on the clock or CLK side rises from 0 to 1. Now, if the input side goes from, say, 1 to 0, or it's maintained as 1, or it's maintained as 0, the output is not executed. So think of it as a one-shot instruction set if you're familiar with Allen Bradley products. Now, on the output side, I'm going to call this coil underscore 1. And what I'm going to do as well is, just so we can see our entire width of the interface, I'm going to just adjust my cell width. Okay, and in addition to this coil 1, just on the bottom side, the next rung here, because coil 1 will actually only energize once, we're going to just add an add int instruction so we can see a variable increment by 1, some integer variable. We'll call this int1. On the output setup, use the same variable, and then on the int2, I'll make it just 1. So what this means is every time this add integer instruction executes, then it's going to add 1 into integer and then add it back into itself. So it's just basically compounding on itself. Now let's accept the edits, and before we do anything else, let me explain what we've done here. So from the first rung, moving from left to right, we have a horizontal wire to energize our R trig instruction so it can actually execute. We have the normally open contact with variable name execute trigger, which is tying into our CLK input, which is our rising edge. And then on the output side, our Q is tied to a single coil called coil underscore 1. And then on the following rung, we're using that coil 1 variable tied to a normally open contact, which then executes an add integer instruction. Now, as soon as we set this execute trig to 1, which I will, just hitting F12 to toggle the state, we can see here that this R trigger has executed because the input has risen from 0 to 1. Therefore, the output has executed for one scan as a single pulse, and then continuing down the line here on rung 2, when the PLC scan hits rung 2, we'll know our coil 1 is energized because of the previous rung execution. And then because it's energized, the add integer instruction will execute, and then 1 will be added into the integer 1 variable and then back into itself. Now we can see here, because we're maintaining our execute trig variable as boolean 1 or on, we notice that the R trig is not executing because, again, it only executes on the rising edge. So if I were to make this a 0 by toggling it off and then toggling it back on, we'll see it produce a rising edge, and therefore the R trig will execute, and we have another yet increment made to our integer variable. And we can do this on and off, and just see it increment the variable. That's basically an R trigger. Now the inverse is true when we're using a F trigger, or falling edge trigger. It's essentially the same with the exception of it's detecting a falling edge as opposed to a rising edge. So this means a 1 to 0 as opposed to a 0 to 1, which we just demonstrated. So let's call this their function block f trigger. And everything else stays the same, that's fine, and we'll accept the edits. Okay. And now that we have created those edits, let's just reset our integer variable, set to 0, and let's execute this trigger. So right now, our Boolean variable is 0. If we energize it, we'll see no change because we're looking for a falling edge, meaning as soon as this falls from 1 to 0, then the falling edge trigger will execute. And there we go. So we can see it's executed just as beforehand, a single pulse output energizing coil 1. The coil 1 variable is associated with an only open conic on the following the following rung, rung 2, and as a result, power flow is passed to the add integer instruction to add 1 into our int1 variable. And we can toggle this every single time, but we can see that every time it falls, it adds 1. That's basically it when it comes to triggers. Now let's deal with up counters and down counters. So I'm going to make just some changes here. Let's create a blank canvas so we can start from scratch. And let's start off with an up counter. So up, I believe it's up CTR is the instruction. And this is a function block, so we got to get our name. We'll call it up counter. And let's go ahead and ensure that power is passed to the counter each time we want the counter to execute. And we're going to execute this on I'm going to call this counter execute. Now, before we jump any further, when it comes to up counters, it has a couple of inputs and a couple of outputs. So when power is passed to the counter from the first horizontal or the topmost horizontal wire, that's basically telling the counter every time you pass power to increment the counter by 1. And in this case, we are incrementing because we're using an up counter as opposed to decrementing had we been using a down counter, which we'll be covering shortly. And on the input side, we have two inputs. We have R, which is essentially just a reset input. So when power flow is passed, it basically just resets the current value of the counter. And then PV is just standing for the preset value, meaning whatever value we're trying to obtain for this counter, once the current variable, the current value, reaches the preset, then power is actually passed to our output. So I'm going to just make this coil, say, counter underscore done. Oops, okay, I totally messed that up. Let's call this counter is done. And on the reset side, let's just copy and paste our counter execute normally open contact and just rename this, call this counter reset, and then just make sure we've closed the gap with the horizontal wire. And in this case, let's say we want to count to 10. And in terms of the current value, we'll just call this counter underscore current underscore value. Okay, so let's accept these changes and allow the PLC program to update. Okay, so right now, our counter's value is 0. Now, if I toggle the counter execute variable, we can see that power is passed and only a value of 1 is actually written to the counter. So in this case, we're starting with 1. If I de-energize my counter execute variable and I pass power again, now we see the counter is incremented to 2. Now, it's important to note too that as well, while power is passed, it also acts as a rising edge, meaning the counter will not increment again until we lose power on the input, and then we have power again. So on the rising edge, it's basically only allowing it to increment on a rising edge. Now, if we want to count up, we can just keep toggling this until eventually we'll hit 10, whereupon the output will execute because only upon our preset variable, a preset value is equal to our current value, then power is passed to the output, and we can see now power is passed. Now, suppose we were to continue toggling our input, we'll notice that the power is continually passed because we've basically hit our limit. We've hit our preset value. In this case, the output will actually be maintained, meaning we'll maintain on, or power is passed, until the counter is reset. And as mentioned, we have this little counter reset variable writing to our R input. So if I reset it, we can see the counter is now reset to 0, and power is no longer passed on the output. Now, it's also important to know that if we had the counter reset, input as 1 whilst we try to execute the counter, nothing's going to change on the counter's increment because we're constantly resetting the state of the counter. So just ensure that our reset is off, and now we can begin counting up again. So that's basically an up counter for you in a nutshell. What we're going to do is we're going to copy all this, and just in the following run we're going to paste, and I'm going to show you a down counter. So we're going to just replace this instruction with the dn counter this time, and let's replace the function block with down counter. Now that's okay, we can keep this counter reset variable, that's totally fine, but this counter is done because we're using it on the aforementioned routine. We're going to call this counter done, just so we're not using this in another location where it might be overwritten, which we're not. And we'll just keep the 10 here, and we'll just rename this output, call this counter down current variable. Okay, now let's accept run changes, and you're going to see a little difference. Instead of counting upwards, beginning with 0 until we reach the until we reach the current variable or current value equal to 10, whereupon our output is energized. Instead, if we execute this counter, we can see, if I reset it, we always begin at the preset value as opposed to 0 if we're doing an up counter, because in this case we're using a down counter, meaning we start at the preset value and we count down until it's equal to 0, whereas when it comes to an up counter we start at 0 and we count up to until the current value is equal to the preset value. So if I go ahead and just execute this counter, we can see we're counting down every rising edge, every scan, and eventually we'll hit 0 and the output is energized. Now, it's an interesting effect too if we continue energizing the counter execute variable, and we can see now we're at -2, -3, -4, -5, and so forth and so forth and so forth. But the output has executed because we hit 0, and therefore we're maintaining that output as true. So at this point, what you'd want to do is just simply reset your counter. As beforehand with an up counter, we have the same inputs. In this case, our R, which is our reset input. I'm going to reset it, and we start back at 10. Now if I hold the reset in while trying to execute the counter, we just hold at our 10 because we're constantly resetting the counter as we're constantly passing power through the R input. And that's it. That's basically counters in a nutshell. Let's start now with timers. So let's clear off our canvas, and we're going to start from scratch. And that's fine. And we're going to clear this off as well. And let's just accept these edits. And there's going to be 3 timers we're going to be covering. One's a timer off delay timer, and one's a timer on delay timer. So with a timer off delay timer, it's a T off instruction. So I'll just create a T off, and it's very important that we always pass power to the timer at the very top. If you don't pass power, the timer is not going to operate correctly. This is different than up counters and down counters. Now on the right hand side, we're going to create a coil and call this timer OK. No, not timer on, timer OK. And on the input side, we're going to just use a normally open contact and call this execute_timer. And on the preset time, I'm going to just make this 10 seconds. And now notice I put 10,000 because our preset time is in 10 seconds. So this is in milliseconds, therefore 10 times 1,000 milliseconds per second is 10,000. And on the elapsed time, we're going to just call this elapsed time, like so. And then finally for the T off time, we're going to call this T off timer. Okay, now just a recap. So let me just accept these wrong edits, and we're going to recap what we've just done here. Now the T off timer is a timing off timer. It's a timer off delay timer actually, timer off delay timer, and it has a couple of inputs. One is our in, which is power flow to allow for the T off to begin measuring time. Our PT is the preset time where the counter will time to. ET is the elapsed time, so you can keep track of how much time has passed based on the preset time. And then once the elapsed time is equal to the preset time, then the timer is finished. Now when it comes to off timers, it's a little weird. It's the inverse of on timers, meaning as long as you're not timing, then the output is, as long as power is passed to the timer, then your output is energized. But it's a timing off delay timer, meaning if you lose power on the input, then the timer begins executing. And we can see there are 2 seconds, 3 seconds, 4 seconds, and once the timer is completed, only then is the output disabled. And as soon as power is passed again to the timer's input, the in input, then our output is passed. It's energized. So energy is passed, or power is passed to the output. Now, if I were to copy this instruction and paste it just below it, and let's use a timing on delay timer, and let's just call this ton_timer. Timer. And we're going to change some of these so we don't have overlaps. Call this ton elapse time. And let's call this timer OK2. Okay. Now what's going to happen here is, as long as power is not passed to the timer, then our output is de-energized. Whereas, as we saw with the off delay timer, as long as power is not passed to the input, the in input variable of the timer, power is well, in this case it's just executed. So as long as power is not passed to the timer and the timer has not finished, then your output is energized. And as soon as your output is energized and the timer has finished, then the output becomes de-energized. Whereas for T-on timer, as long as the timer is not timing and the output is de-energized, then your output is true. But as soon as we energize the input, and now our timer is timing, the output is de-energized until the timer finishes, whereupon the output will energize. So there we go, the timer has finished and now our output is energized. So they're basically inverse instruction sets, just like we saw with the counters and down counters. One requires that if no power is passed, your output is energized and it will count to your preset time, whereupon the output de-energizes, whereas the on timer is a little opposite, meaning the output is de-energized as long as the timer is not timing and is not completed, and as soon as the timer completes itself, the output is energized. Cool, so that's basically it for T-ons and T-offs. We're just going to wait for this transition so you can see the output again. And there we go. And now we're going to look at the final timer, which is a little unique. It's called an on-delay stopwatch timer, or on DTR sec. So we're going to create an on DTR sec, and there's other variants. There's hundredths of seconds or tenths of seconds. We're just going to use the seconds one, and we're going to give this a name, call this on DTR timer instruction, and we're going to just make sure we have a horizontal wire here, and we're going to put a contact here, call this execute on DTR. This is our reset instruction, so we're just going to create another normally open contact here and call this on DTR reset. And let's just have our preset variable, our preset time in, say, let's just have this 10,000. And our current value is, say, current value timer. And on the output side, let's call this on DTR done. Okay, so let me explain, we'll recap before we execute. So the on DTR sec instruction is basically a retentive timer that tracks your time as long as the timer is timing. And when the timer is not timing, the time captured is retained until the timer is either reset or you re-execute the timer to then start off where you've left off until you've reached the preset value. So we can see here, we've set our preset value to 10,000, which is 10 seconds, and this is just our current value, which is going to be changing while the timer is timing, and we have an output which executes again when the timer is finished, as well as an R input, which is basically just the reset input for the timer. So if I were to execute our input side, we can see here that our input is timing in seconds, and my apologies, I meant this is actually in seconds. This is not a millisecond timer, so this is like 10,000 seconds, not 10 seconds in milliseconds here. Now if I were to go ahead and pause this timer by removing power to the timer, we can see here that we are retentive. We are maintaining that last capture 22 seconds. And if I just start up again, we can see we're just continuing back where we left off. Now, if we were to go ahead and change this to say 30, because I'm not waiting 10,000 seconds, we can see here, as soon as we count one more second, we've reached our preset value. Therefore, the output should energize. So if I enable our execute on DTR instruction, we can see our output is energized. And now we've met the preset value, and therefore the output is executed. Now, if we were to stop executing this timer, the output is maintained as on, power is continually passed to the output until we reset the timer. So if I reset it, now power is no longer passed, and had we held the reset in and tried to execute the timer, just like we saw with the up and down counters, this timer will not execute until we remove power to the reset input, whereupon the timer will begin counting. Now, once we count to 30 seconds, then the output will be executed, whereupon you could do any kind of further sort of logic downstream. And that logic could even involve, okay, once the timer finishes, maybe you want to add 1 to an integer variable, and then you would basically write to a coil which energizes the on DTR reset variable so that you want to reset the reset the timer. And that's it. So that's basically timers, counters, and rising and falling edge triggers in a nutshell. I hope you've enjoyed this video and found it informative, and thanks again for watching.